squared. So this thing right here, and the horizontal line y equals 2. So it looks like, yeah, they already labeled that. That's R, and then the other one is S. Okay, and then they want you to do some stuff here. So first thing is to find the area of R, it looks like. That's what letter A says.
Yeah.
So letter A, to find an area, it's the integral. You need the left bound and the right bound. Okay, so in this case, we don't know those points. Okay,
Yeah.
and to find them, you have to set, we have to do that off to the side here. You have to set 2 equal to e to the 2x minus x squared. And I'm going to guess, well, it does say calculator, okay. I'm going to guess that you're going to need a calculator to do it. Like, it's not going to be by hand. So
yeah,
let me new share Desmos. Hopefully you know how to use this graphing tool. You can definitely use your calculator, but just for the speed today, I'm going to do it here.
okay.
If it's really unclear how to do it on your calculator, we can do that as well. So let me graph it correctly. All right, and then we get those 2 points. Actually, they aren't all that nice. Okay, so those are the 2 bounds that we're going to use. I'm going to snip that back in and go back to the other screen. Have you used Desmos before?
Yes.
Excellent. All right, so go back. So those give us the limits of integration. 0.4446, 1.554. And then in general, it's top minus bottom for x integrals.
Okay.
So the top in this case is e to the 2x minus x squared. The bottom is 2. And then dx, like this.
Okay.
So that's R. And then how comfortable are you using your calculator for that? I think it's math 9 FN int for that. Do we need to go through that?
Oh yeah, no, I know how to do the integral.
Okay, so that
should work.
That's that. So now let's do S.
Okay.
S is another integral. It's the region though from, let me go back actually and grab this picture again. So this time it's actually 3 sections. Let me go grab this picture again. Maybe I'll go grab this one. I'm gonna actually snip in the graph here because I think it'll be a little clearer
Okay.
what we're doing. So it like at first glance you might think, well, it's just 2 minus 1, but if you look at the graph here, it's actually kind of 3 regions. It's what I'll call S1, S2, and then S3. Is that okay? All right. So S1 in this case is from 0 because that's the left bound. And then the right bound is this 0.446. And then top is that E again. It's E to the, 2x minus x squared.
Yeah.
Minus 1 dx. S2, and you could write this as an integral, but it's really just an area, but it's the integral from 0.446 to 1.554. And then your top function is this y equals 2 and y equals 1. So it's 2 minus 1 dx.
Okay.
Okay, and then S3 is the third. You're going to integrate from 1.554 to 2. It's always using the x coordinates. The top minus bottom, it's back to this other one, e to the 2x minus x squared minus 1 dx, like that.
Okay.
Is there anything about that you don't feel like you could do now that you've seen it work through?
No, I feel way better about that. Can you show me how to get the bounds like on my calculator?
Yes. So give me just a moment to get my graphing calculator up, and then I will share that. All right, so the calculator I have, the virtual one here is a TI-83. There's minor
Mhm.
differences. You're probably using a TI-84. You go to y equals, and you want to enter in that first one, E.
Okay, so I should just like plot it on the graph and then
Yes,
find the
yes.
point. Okay, cool.
And,
I didn't know if there was like a different way that I can graph it, so that should be fine. I
um,
wasn't sure.
let me just, if you're okay with it, just really quickly go through how to find the intersection if you don't already know.
Yeah.
It's second, and then
Okay.
it's calc here,
Mm-hmm.
second calc, and it's 5. It's the intersect.
Okay.
And if you haven't used it in a while, it makes you choose something on the first curve, which could be either one,
Uh-huh.
and then you choose something on the second curve. And they don't have to be that close. They just have to be sort of in the neighborhood.
Yeah.
Actually, I got the wrong curves. And then you always guess at that point, and it'll tell
Mhm.
you 0.446.
Okay.
Now I would zoom in on the first quadrant here, but
Yeah.
that is it. That's the only way to do it. It makes you appreciate technology, because this calculator is very, very antiquated, and Desmos did it way faster than
Yeah.
here. All right.
Okay, perfect.
And you can integrate on here, math 9. There's this is truly a calculator question. There's no way to do it by hand.
Yeah. Okay.
All right, so that is question 7.
Perfect.
So you tell me
Um,
where you want us to go next.
it's another calculator one. It's number 2 with the particles.
Okay, so a particle P is moving along the x-axis.
Yeah.
That one there. Okay. All parts.
Yes.
Okay. Did you take physics at any point yet?
I took it last year online, so it was not exactly true physics, but
Okay. Yeah, this is actually a really good physics type question. So if you're seeing my screen, I've got it snipped in.
Mhm.
They want you to find the velocity. So the velocity is given, and they want you to find the position of particles P and Q at time t equals 1. So the thing that you
Mhm.
have to remember is position is the integral of velocity. You remember that?
Yeah.
Okay, but then there's this, like, one of the fundamental theorems of calculus where you have to take into account the initial position.
Mhm.
Okay, so the answer here to, like, what is the position of P at t equals 1? P at t equals 1 is P of 0, which is that initial position, which is 5, plus the integral from 0 to 1 v of P dt. Okay, so the fundamental theorem of calculus, one of them, parts something, says to take that initial value and add it to whatever you get between the area of it in the time window that you care about, and you care about it at time t equals 1.
Okay.
So when you're, if you recall, when you're given v and t, and you're given some graph here, the
Mhm.
area under the curve is the distance traveled,
Yeah.
and that's what this part over here on the right is. But that does not take into account where you started.
Okay.
That's why this additional step is here. So in practical terms here, v of p is sine t to the 1.5 power dt. So the position where it is at 1 is its initial position 5 plus this integral from 0 to 1.
Okay, that makes sense.
And it all comes from this right here, which you don't need to know, but you do need to know how to find it. So what most students do would do this part here, and they forget to add 5. And on
Mhm.
the AP, that might be like a 1-point deduction on this free
Yeah.
response question.
Okay.
Okay, so let me know if you want me to, if you want me to put this in the calculator or work it out. This is
No,
math,
that
9
should be
again.
fine. Yeah. Thank you.
Okay, so Q at time 1 is really similar. It's the initial position of Q,
Mhm.
which you can see is 10, plus the integral from 0 to 1. It's a different velocity functions VQ of t dt. So it ends up being, what is it? T minus 1.8, 1.25 to the power of t dt.
Okay.
So it's always your initial starting point, initial position plus an integral. If it wanted it for the first 2 seconds, you would do it from 0 to 2, and you would get some number that you add to this. And it could be that it adds or subtracts. Like we don't really have any way to know whether this is positive or negative unless we graph it. So don't be surprised if it's, you know, more than 10 or less than 10. It could go either way.
Okay.
Let me know when I can move on to part B.
Oh yeah, we're good. I think I got down. Thank you.
Excellent. Okay, our particles P and Q moving toward or away from each other at time t equals 1. So the answer to this is it's not really a trivial thing. So it's like we know that P is 5 away from home. That's where it started, and Q is 10 away from home.
Okay.
So think about, like, your friend is 5 minutes from home and you're 10 minutes from home. If your friend is moving towards home, but you're moving away from home, that's one scenario. If you're both moving towards home, that's another scenario. And all of that comes from the velocity. So we need the velocity of 1 for each of these. And because they give you the velocity, you just evaluate it. Okay, so in this case, it's sine of 1 to the 1.5 power. And make sure your calculator's in radians, because there's probably never a problem in this class where it'll be in degrees on the AP. So sine of 1 is 0.84. This is positive. Okay. And then VQ, what was that? It was t minus 1.8, so it'd be 1 minus 1.8, 1.25 to the power of 1. So it's going to be negative something. Let me just get the actual number. 1 minus 1.8 times 1.25. So negative 1. All right. So here, you know, like here, let's consider this to be home right there. Here's P and here's Q.
Yeah.
P is moving right and Q is moving left.
So they're moving towards each other.
Yes. But if Q was over here to start, they would be moving away. So it depends on where they've started during that time.
Yeah. Okay.
There's also another little component here. I guess this is not complete, I suppose, is we really needed these numbers from here because they moved in the first 1 second. Like, we don't know whether P moved one direction or the other. It probably is still this answer, but we really should have figured out their new position there, which is one reason we probably should have gotten these numbers. But it's essentially the same analysis.
So we need
these numbers, right? Or
with t being 1.
Yeah, because what it does is it changes where they started. I actually don't know, and that's
okay.
And so let's get it, because that's what I was trying to imply here. Like, it could change this.
Yeah, because if they're in a different position to start.
Right. After 1 second. So do you want us to get these numbers, or do you feel like you understand what you would do if you found these numbers?
I would just, whatever I got when I plugged in 1 to the original equation, like the things we found in part A,
yes,
that's just what I would.
Those are your new starting points, so to speak.
Okay. Just like to think about it in your head.
Yes, yes.
Okay. Okay. Then we don't need to go over it. I'll be fine.
Okay. All right, part C. Part C. So if you do take the AP, there are parts of these free response questions that you can answer even if you don't know how to do other parts.
Yeah.
And this is one of them. This one is asking about acceleration. And so acceleration is the derivative of velocity.
Uh-huh.
And you're given the velocity of each. So the velocity of P is sine T 1.5 power. Your acceleration is the derivative of this.
Okay.
So it doesn't have anything to do with anything we've done thus far. Very different.
Yeah.
So derivative of sine is cosine. Chain rule says you have to take the derivative of the inside function, 1.5 t to the minus, I'm sorry, positive 0.5 power. And then they want you to evaluate it at 1.
Okay.
And you know, I don't really know what this is because.
And this one would be for Q, so it'd be the other equation, right?
Sorry, yeah, I did it for P. You would want to do it for Q. So
Okay.
Q is product rule. So your acceleration is, depending on how you do it, you know, there's different orders here, but the derivative of the right is itself times the natural log of the base plus, and then you take the derivative of the left, which is actually just 1, keep the other function here. And so you evaluate it at 1 and you get some number for that. I believe the AP also doesn't, I don't think you have to actually calculate it. I think if you show this, that's sometimes good enough, or it's a small deduction. So depending on like time, you may or may not want to actually calculate it. We did need it, for example, in part B, but you know, be okay.
Okay, perfect.
All right, is this okay?
Yeah.
Clear? All right. So part D, it says to find the total distance. And at first glance, you might think, oh, I'm just going to integrate. It's a lot like part A. The problem is if there's this discussion at some point, total distance, total displacement. Remember that? Like if you're on a track and you go all the way around, your distance is 1 lap. But if you start and stop here, your displacement is 0. And so you got to be careful here that all the positive distances are counted positively and all the negative distances are counted positively. And the only way to do that is to graph the velocity functions that you were given in the beginning of the problem and see if they cross the axis between 0 and pi.
Okay.
So I'm gonna go to Desmos and I'm gonna just graph this and see if it does that, and I'll snip it in for you. But you would want to do that in your problem to make sure that it was okay, because you would potentially make some mistakes here on this. So yeah, actually we just want to go from 0 to pi, and then the other one is sine, what was it, t to the 1.5 power. Let me get these snipped in here. All right, so I'm going to snip in this graph. Hopefully. Cancel. All right, so the graph here, and to change that it only graphs the part that you want, you just put it in curly braces, the domain. I think the first one, this was P, this was Q. I may have graphed backwards.
Yeah.
But you can see that P from 0 to 2.145, that's positive.
Mhm.
And then the area below to the right of 2.45, it's negative. So you have to break that up into two integrals. So the total distance for P is going to be the integral from 0 to 2.145. And then it's that V of P function. And what I don't recall is if you can actually just like refer to it as V of P, or if you have to actually say, you have to actually give it like this.
Mhm.
And then you subtract this area because when it's below, it's considered negative. 2.145 to pi sine t of 1.5 dt. Okay, and then the area of S, or the total, these added together, the S crosses at 1.8. So that first area is negative, so you would negate it. You can also do some things like flip the bounds, which I
Mhm.
wouldn't recommend, but that would be also acceptable here. And then you add the area from 1.8 to pi for the other one.
So since this one's just particle,
It's just one of them. I
it's
didn't
just
even, oh, it's
particle
just P. I'm sorry, I did them both.
That's okay.
But you can
So
see they're the same,
yeah.
idea. You have to figure out where
So
they cross.
we're is it like subtracting the second interval thing because it's negative? And so normally if it
Yes,
was
yes,
okay.
yes. Because the like this first part is like you driving away from your home and then
Mhm.
stopping at a, you go to the mall or something or a store, and
Yeah,
then you're coming back.
you're still traveling
You're
distance.
still traveling. Your car still knows that you went a distance. Your
Okay.
odometer tells you
And
that.
so that's like its negativity is causing the subtraction. It's not like you subtract.
No, this integral by itself without the
Uh,
negative comes out as a negative number. So by subtracting it, it adds.
okay, so
So if you went to your calculator and did math 9, 2.145 to
uh,
pi, all of this, you'd get a negative number. But by subtracting it, you would
okay.
undo that. That's all it is. It's no more complicated than that.
Okay. And so if say the graph like had I think it's like a cusp or something, so it went instead of going negative below the axis, it just like went up again.
Okay, so let me so let's keep it really simple, and let's say it was something like this. Is that what you're referring to?
Yeah.
And call that 4. So you in this case you could go integral 0 to 4 plus integral 4 to, I don't know, 8,
Uh-huh.
or you could just combine them, 0 to 8,
Okay.
because
So
it's
as long as
always
it stays above, it's only when it
yes.
crosses the
That's
x-axis in this
yes,
case.
yes.
Okay. 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 Perfect. Thank you.
All right.
Um,
All right. Anything about this that you would like us to go through again?
I don't think so. So for the position at a certain time, you do the initial plus the integral from
Yes,
0 to that time of the velocity.
exactly.
Okay, and then part B, you use the velocity of each one, and then you just plug in the time and, like, compare them?
You need to know how far it's gone in the first second, which comes from part
Yeah,
A, and then that tells you like
where it's
where
starting.
where to start, and then depending on where that is, it could be both moving away or toward, or one.
Okay, got it, and then the third one, um, you just find acceleration
Yes,
by taking the derivative of the velocity.
yes.
Okay, and then the last one we just did. Okay, cool.
Great.
I think the only other one that I really wanted to go over right now was um, part C of the number 3, the one about a spinning toy.
Right. Let me see here if I can find it. Is that on page, which page
Um,
of the
it should be
PDF?
the page after the one we just did. Or actually, it might have printed differently for me.
Yeah, see, I'm seeing, okay, oh, there it is, there it is. Yes, it is question 3.
Sorry, it's
right.
the person who made this warned us that it was bad formatting, so I apologize.
Yeah, so should we go through all parts of this?
So I did B, and then I'm like halfway through A, so we can do A if you want, and then we can also do C.
Okay, A may help here. Let me snip it in and then
Okay, cool.
look at it. All right, so if you're seeing my screen, hopefully you're seeing company designs spinning toys using this function. And I guess we're supposed to assume that that's the function there. C is a positive constant, blah, blah, blah. Okay, each spinning toy is in the shape of a solid revolving around the x-axis. So I like to show like which axis it's revolving around. I think that could be helpful. But the first part here, it says find the area of the region in the first quadrant bounded by the x-axis and the graph of y equals cx thing here for c equals 6. Okay, so the area is just an integral, this area into the curve, 0 to, and we need to know this point right there.
Yeah.
Do you know how to find that?
Is that when you usually that's like when you set them equal to each other, right? If it's
Right,
like
but
two
this,
different, but this one's just 0.
yeah, you just set it equal to 0,
Yeah.
and it's actually always 2 in this problem because of this root thing. So you could graph it, but it's going to be 2. So that tells you the upper bound. You got to get the right upper bound, or you can't do any of this. And then how the way to do the rest of it to find the area under the curve is it is top minus bottom, but since your bottom is the x-axis, it's just this. Yes.
Okay.
In the previous problems, I was not very good about writing the dx or dt. Just that is a point of emphasis on these exams, is to make sure you have that in there.
Okay.
All right, so great. We've dealt with the application. How do you have any idea how to integrate this as it is?
Yeah, it might take me a little bit, but I think I can do it. I'm pretty sure.
Okay, so this is a U substitution.
Okay.
And the reason is because the derivative of what's here undoes this. Okay, and hopefully you've seen this. If you're in chapter 8, I assume chapter 7 or 6 had some of these in there.
Yeah.
So du is minus 2x dx. You solve for dx, so dx is du over minus 2x. And from here, you substitute in. So 6x, you don't have a substitution for. Whoa, I had a little glitch here. I'm sorry. There it is. Okay. And then dx is du over minus 2x. Okay. So notice the x's cancel. So if you've done this correctly, the x's should go away. And then if you've seen U substitutions before, sometimes you change the bounds.
Yeah, so that
as
you can
part of,
plug in right away.
yes. And so this case, you put the lower bound into this 4 minus 0 squared, that's 4. You have to put them in the same place. And then U of 2 is 4 minus 2 squared, which is 0, which looks odd, but just go with it. You may find it like it does work out nicely doing it this way. All right, so antiderivative of this, you add 1 to the exponent, you divide by the new exponent, you bring the -3 down, and you have the limits of integration that you're going to evaluate at.
Okay. Usually
it's a good idea to simplify here. So sometimes students are already bringing this up and flipping it. It's 2/3, but you got the -3 there. So it's -3 times 2/3. U to the 3 halves, still from 4 to 0. So it ends up just being -2 U to the 3 halves. And at any point, I mean, you could just your calculator, but we'll do this by hand. So this is -2 times 0 to the 3 halves power minus minus 2, 4 to the 3/2 power. I don't remember if this one was by hand or not. So this is 0. These two make a plus. 4 is really 2 squared to the 3/2 power. Exponent to an exponent, you multiply them. So it's 2 over 1 times 3/2. And the 2's cancel. So it's 2 cubed. 2 cubed is 8 times 2. So there's a lot of 2's, a lot going on here, but it ends up being 16.
Okay.
When you're all said and done.
Okay, that makes sense.
Now, it says that it's something about X and Y are being measured in inches because it's an AP question and it's asked for area, it's inches squared. So you can do that. All right, so then part C. Part C. All right, so for another spinning toy, the volume is 2 pi cubic inches. I believe it said that they're rotating around the x-axis again. So let me grab just the picture one more time. So this one, they're giving you the final answer and you're working backwards.
Okay.
So you have to write the formula for volume. Is this a disc or a washer? And if you're not sure, I'll explain, but if you want, you can jump in and tell me.
No.
Okay, so this is a disc problem because the way I say it, there's no gap. There's no gap between this region and what you're revolving around. So a disc problem has a formula, a to b pi r of x squared dx, and your r of x is really the y. It's really this right here.
Okay.
Okay. And let's see here. Okay, so we know the answer. We know the answer is 2 pi, but we got to do something to solve for it. So this is the integral from 0 to 2. The reason it's 2, as I mentioned, this is always 2 there from this right here. The pi comes from the pi, and then there is a c, so it's cx square root 4 minus x squared, but you square all that. And you can do it off to the side or you can do it inside the integral. It's whatever you prefer.
Okay.
You get to make more choices in math the more you take. All right, so I'm going to simplify this. C squared x squared 4 minus x squared, like that. And then I'm going to bring the c out because it's a constant. It's going to be in the way when we're integrating. So this becomes the integral from 0 to 2. You can actually distribute this in. 4x squared minus x to the 4th dx. And again, we know this all equals 2 pi, or so they say. All right, so antiderivative of this, you got 4/3 x cubed minus 1/5 x to the 5th. And then you evaluate from 0 to 2. Whenever you have a polynomial, the 0 always goes away, so you don't even have to evaluate at that.
Yeah.
But you definitely got to evaluate at the upper bound here. And if there's a lot of fractions, doesn't really work out nicely usually. So this is 8, 32 over 3 minus 32 over 5 pi c squared times this. So you could, you don't have, I don't even know if you want to simplify this, but if you did, you could just say c equals, the pi's cancel, 2 over 32 over 3 minus 32 over 5 square root. And be done. That would be okay.
Okay.
Now, if you actually want to do it, you can. Maybe it works out nice, but if you've gotten this far, you definitely understand how to do this. And if you do have a desire to take more math or to go into engineering or anything like that, physics classes, they actually tell you to stop. They say don't just we know you understand it by now. At this point.
Okay. And so, okay, so for a disk, it's always pi and then little r squared, r squared.
Let me just make a quick sketch to show you. So let's say that y equals the square root of x.
Mm-hmm.
And I'm gonna just, this is a blown up graph. It has this kind of shape to it.
Okay.
And that's the 0.11.
Mm-hmm.
Okay. So there is no gap between it and the x-axis.
Mm-hmm.
Okay, so this is a disk problem. I was actually on social media, and I think it was Twitter, and someone said they actually prefer to call this the pancake, because pancakes can change size, but they're always solid. I don't know if that's a better visual for you.
Okay.
But a washer problem, if we look at something like the square root of x and y equals x,
Mm-hmm.
there's going to be a region. So again, blown up looks like this, and there's that. So this is y equals square root of x.
Yeah.
This one is y equals x. And you can see that there's a gap between here. And this is what is called a washer or a ring problem, or maybe even a donut, if you like. But in that case, they have two radii. They have big R.
Yeah. Because it's r squared minus little r squared times.
That's right. And then little r.
Yeah. Okay. And
And
so little r is always the bottom
if you're going in x.
if you're going in x. So can you show me an example in y?
Yes, we can actually use this same problem here.
Awesome.
So we'll go. I'll just it'll be given like this: y equals the square root of x, y equals x, and it'll say revolve around the y-axis.
Mm-hmm.
Okay, so whenever you have a y-axis problem, you generally want to solve for x.
Okay.
So this first one becomes x equals y squared, and this one on the right is x equals y.
Mm-hmm.
You graph them exactly the same though as you would if they were an x. And again, this is just blown up here. This is the y equals square root of x, and this is y equals x. And so it's this region in here, but we're going around the y-axis.
Okay.
Okay. And you noticed I did this in the previous one. I strongly recommend like identifying big R,
Mm-hmm.
and then identifying little r. Okay.
Okay.
Now,
So little r is the line that's closest to the axis you're revolving around?
Yeah, yes.
Okay.
Exactly. So y-axis though is left minus right. And that's your big R squared minus your little r squared. I'm sorry, this is completely wrong. It's right minus left. Why did I write that? This is how you remember it. If you were to rotate like in graph, if you were to switch, like you can actually rotate the axes 90 degrees and then it still is top minus bottom. But since we don't do that, we prefer this orientation. It's always right minus left when it's a y-axis.
Okay.
X-axis is always top minus bottom.
Got it.
Okay. So this time the functions are in terms of y. Okay, so you're integrating, and some books do this. They go like C to D, but it's really whatever your two limits are. So in this case, it's 0 to 1, and you get that from setting them equal and solving.
Yeah. Okay.
Okay, so in this case, it's 0 to 1. Your big R is x equals y, so it's y squared. That's your big R minus the other one, which is square root of x, but you're supposed to use the x equals y squared. So this is your big R and this is your little r, dy times pi.
Okay, that makes sense.
And then you work through that as needed.
Okay.
Is there anything else? We got some time left if you would like to look at. No, we got another lesson scheduled on Sunday.
Yeah. I think I had. So do you have any advice for like cross sections, like in the on one of the last pages with the cosine and sine graph that's shown, and there's like a little shaded part between them.
Yes.
So in class, my teacher showed how to do the cross sections.
Mhm.
Can you like just do another example of something like that?
Yeah. So let me pick. I mean, these aren't great, but let's say it's y equals x squared.
Okay.
So the graph of this, and again, this is exaggerated, and we'll call this point 2, 4. Okay.
Mhm.
So let's say let's say the cross sections are made with the x-axis.
Okay.
Okay. So like this right here is an example of a cross section.
Mhm.
Okay. But what could happen is from here, I could say, oh, it's a circle. It's a
Okay.
semicircle. It's a square. It's a triangle. It's a right triangle. It's a isosceles triangle.
Mhm.
So lots of options. What you have to do is come up with the area function.
Okay.
And so like this is a side. Okay, so like if I draw a circle, and I tell you that this red thing is the radius,
Mhm.
you have to be able to tell me the area of a circle is pi r squared, and realize that in this case, the radius is x squared.
Okay.
Okay, but I could just as well say, oh, they're semicircles, and the red part is the diameter.
Uh-huh.
So I'm going to draw that in here. So the area of a semicircle is pi r squared divided by 2, but the red isn't the radius, it's the diameter.
Yeah.
So the radius is x squared, but you divide it by 2.
Mhm.
Okay, and if I said, oh, for here, this cross section, let's say it's a square. So here's your square. This is probably the easiest one because it's so direct. But if I tell you that that's that,
Mhm.
the area of a square is base times height, which would be x squared times x squared.
Okay.
Okay. Now this goes on and on, right? Because there's a
Yeah.
bunch of geometries. Once you figure that part out, it is always the integral from a to b, whatever your
Mhm.
bounds are, that area function you just found dx.
Okay.
So like in the square problem, it's x to the 4th. That goes right there.
Yeah.
In this other problem, this would go there.
Okay.
And sometimes I want you to draw it, and it's a little hard to draw, but
Yeah.
if I hope this visual helped you to see, like, that's what this line segment is meant to represent. Like it could be anything. I mean, it could be radius, diameter,
Yeah. No,
side. I
that
mean,
makes a lot of sense.
yeah. I mean,
And then if you were to find like the volume
this
of,
is the volume.
oh, okay.
The volume is you take whatever function you get and you
Yeah.
integrate it from whatever the bounds are.
Okay. Got it. Awesome. Okay. Thank you.
Great. Is there anything else you would like us to look at or talk about?
Can we do 1D on the first page?
Sure. Calculator. Okay, great. Okay, I believe this is just asking for an area. Is that right?
Mm-hmm.
Okay, so the area is, when it's with the x-axis, it's just the y function, 1 plus natural log cosine to the 4th x dx, and they give you the bounds. So you just go minus 2/3 to 2/3. So this is purely a calculator problem.
Okay. And then you just plug them in.
Yeah, I mean, if it asks for like distance or total distance, we might care about this. Um, we might want to break this up into two integrals, but it doesn't. It just is area. So
Yeah.
you just integrate and you get a number and move on. It's so a lot of the questions you asked me today were calculator problems. I know we're going to do another lesson, but how comfortable are you doing the ones by hand, like C or 1C
Yeah,
or
definitely like the ones with graphing were pretty easy. It took me a little bit to get number 10, but I was talking to my teacher, and because I was like trying to solve the whole thing,
Mhm.
but she said that on the test that would be one that we would just need to set up but not evaluate. So
Yes,
that
yes,
makes it a little easier.
yes. Okay, yeah. Just try to work on what you can. If you've got time, I'll send you the notes here in the next few minutes.
Okay.
I upload the screen recording to YouTube, and you can look at it later if you want. But
Awesome.
this is kind of the format of the lesson, so I hope it
Perfect.
worked for you.
No,
We can
yeah, great.
Awesome. We can do whatever you want next time in terms of working on more problems or whatever
Yeah,
you need. I
probably
can
just want to do more like questions like the one from the PDF I sent you.
Okay. I can also make up questions based on if you're like, hey, Matthew, I really want to do another one like 4F, whatever
Mhm.
4F is. And I'll be like, sure. And I'll make some up like that for you to work on as
Okay,
well.
awesome. Yeah, I can email you like specific ones I really want to work on.
Great. So the lessons are 50 minutes. So that does take us to the end of our lesson for today.
Okay.
Thank you so much for scheduling, and I'll see you next time.
Yeah, thank you. Have
Have
a
a
good
great day.
one.
Bye now.
Bye.